Okay, welcome to the NUPOC video study guide number 33. Let's take a look at question 8 in the graphing math section of guide 1. So here we just have this fourth order polynomial, and the first thing I would think to do would be to kind of look for the roots, maybe use the Descartes rule of signs, figure out how many we have, and then maybe use the rational roots theorem. But a couple issues we have with that is we don't have an x squared term, we don't have an x to the first term. And when we go to use the rational roots theorem, we're going to have quite a number of combinations of factors of our x to the 0 term and x to the fourth term. And in fact, we're going to find that this function doesn't have any roots. So it would be pretty discouraging to go through all of these roots, testing them, and then find out that none work. So let's instead just look for critical points and then evaluate at critical points and see if we can gain some insight into the shape of the curve that way. And of course we know it's a fourth order polynomial with a positive sign on the x to the fourth term, so we expect it to sort of be concave up. It's going to come down, it's going to wiggle a little bit, and then it's going to go back up, right? Okay, so let's go ahead and get started. So let's find dy dx here, and this is just going to be 48 x cubed minus 6x. And there's not going to be any plus anything here, actually. So let's just write plus 0, right? And so this can be, we can pull out an x squared here, right? So we'll have an x squared, and this will just become 48x minus 6. Okay. I don't know if any of you can hear it. There's a little bit of whistling and wind in the background. The weather's picking up here a little bit, and I've got my window open, but I'm just going to go ahead and try to finish out this video without getting up to close that, and hopefully it's not too much of a distraction. Alright, so let's take a look at what could make our dy dx 0. So obviously x equals 0 is going to be a critical point. If you move the 6 to the other side, setting this term to 0, and then moving and then dividing each side by 48, we'll find that x equals 1/8 is also a critical point. Let's go ahead and find out if they're minima or maxima by evaluating dy dx in different regions around these critical points. So let's look to the left of the leftmost critical point. So let's look at x equals minus 1. This will equal minus 1 squared times minus 48 minus 6. So this is just going to be minus 54. Okay. So since we have this minus sign, we know we have a negative slope to the left of x equals 0. Now let's look at dy dx evaluated somewhere between the critical points. Let's pick x equals 1/10. Okay, so now we'll have 1/10 squared times 48 over 10 minus 60 over 10. So this is going to be 1 over 100 times minus 12 over 10. So that's going to equal minus 12 over 1,000. So it's a much smaller slope, it's much less steep, but it's still negative. We have this negative sign here. So that's interesting. So even though this is a critical point at x equals 0, it's not a minima or a maxima. It's just a point where the graph happens to flatten out a bit before continuing its descent. So let's go ahead now and take a look to the right of the rightmost critical point. So let's look at dy dx evaluated at, let's say, x equals plus 1. Okay, so this will just be 1 squared times 48 minus 6. So that'll just be 42. So here we have a positive slope, so we know that x equals 1/8 is going to be a minima. Let's go ahead and look at what the function values are at these critical points, and that'll give us a better idea of the shape of the graph. So at y equals 0, we're going to have, obviously that'll just be 8. And at y equals, at y of 0, or x equals 0, that's 8. At y of 1/8, right? Okay, we're going to have, let's see, 12 times 1/8 to the fourth minus 2 times an 8th cubed plus 8. And if you do that out, I have it in my notes here, I did this out earlier, I believe this comes out to 3/128. So it's small, but it's still positive. So if we're coming down from a positive number, we flatten out, we come down to a minima that's still positive and then head back up. We never actually cross the x-axis, so you can see that we don't have any roots for this function. Alright, So now I think we've got enough information to graph it. Let's say that this out here is x equals 1/8. Let's say this is y equals 8. It's going to be a little bit of a distorted graph, but we just want to show what we know about its shape. So this is going to be y equals 3 1/28, right? So the graph is going to kind of come down, flatten out here for a minute, then continue descending, kind of just touch this point here at a minima, and then head back up. Okay? And we could find what our inflection point is here. Turns out it's obviously it's going to be between x equals 0 and x equals 1/8. Turns out to be x equals 1/12. If we wanted to look at that, we could take d2y dx squared, and this is something they don't do in the solutions. We'll get to that in a second, though. There are a number of differences between this and what's in the solution manual. This is going to equal, let's see, 3 times 48. So that is going to be 120 plus 24, or 144, x squared minus 12x. So that's going to be x times 144x minus 12. So it's either x is going to make this second derivative 0, or 144x minus 12. So this, if you move the 12 to the other side, divide by 144, is x equals 1/12, which is what we have here for our inflection point. All right. Now, a couple of comparisons with what's in the solution. If you're following along with the solution manual, right here, right, you can see there's just one error that they make that is propagated through the rest of the function. So here, when they take y prime of this second term, right, this is correct. This is what we have. They come up with minus 8x squared instead of minus 6x squared. Now, the rest of the solution is correct. When they take the second derivative, this becomes 144x squared minus 16x, and so they end up with these other inflection points, and they end up with these other critical points here for the second derivative. So their critical points and inflection points are correct for this y prime and for this y double prime, but this y prime is not correct for this y. So that's why, if you're looking at it, you may say, well, they got 1/6 here, or they got 1/9 here, and we got 1/8 and 1/12. Fairly confident this is the correct way. So anyways, this is just a good walkthrough of how to get the graph from a fourth order polynomial, and just a quick lesson in when you get your critical points, they may not be minima or maxima. They may actually just be a spot, like here, where the graph just flattens out for a minute before continuing to do whatever it wants to do.